So let's go ahead. We go to the home directory, we clear everything. We have already the source file. So now the first thing is let's have a location for you to save your no solvers. So for that, let's create a directory. And then we have WM project. This will take you to the source location of your folder, user directory you want to go. And in there, let's say I create folder of applications and solvers. Please make sure you don't do any mistake in line, in the spelling of this, because later on, then again, you face issue. So what I have done is just created one new folder in my run directory. I can show you. In my user directory, I have created this new folder, applications, solvers. Okay. And WM project source user directory is taking you to this location, my user location. Done. Anyone can say done? Yes. Okay. So now that we have copied, made the solver. So let's copy our. We are going to modify the icoFoam solver. So it's like incompressible solver, and based on PISO algorithm, and we are going to incorporate temperature equations in it. Okay, so U and P will be solved by PISO algorithm, icoFoam, and we will add a new temperature equation. So we will obviously take our Navier-Stokes solver, PISO solver, and then modify it to add the temperature equation. So for that, I'm going to copy my from home solvers. I will copy incompressible icoFoam. Copy it where? We are going to copy it to our new solver location. That is WM project user directory applications solvers, and let's say I rename my new solver as my phone. Any issue till here? Copying this file. Done till here? That's good. So let's go to this new location where our solvers are. Applications. Solvers. I have my phone. So I will go inside my phone and let us check what are the files inside this. So this is very basic solver, just the Navier-Stokes solver. It has found the make directory, create fields, and icoFoam C. So the first step we will do is this replace this C file, because our new solver will be my phone. So I will move my icoFoam C to my phone C. You need to make a new name, because otherwise you will when you will run the icoFoam, you will run your own solver. Difficult to you will replace the icoFoam previous, which is come with by default. So for that, my phone C I am replacing. So now let's go to the make folder. This is the, I think, previous tutorial also you have got some idea when you have do the turbulence modeling tutorial. So we need to edit it, right? So the first thing we need to edit is in the make folder where you are setting the locations of your new files. So here I will, my new C file is my foam, and executable will be in the user bin, user app bin, and then we have this. Our folder is also named as my foam. So please make sure you make these changes to files. Done? Someone? Okay. So we are done that. So okay, so let's check it once again. So we have not modified anything yet. So let's do wmax so that we know that our new solver is ready actually. Later on we will do the modifications. So if I do wmax, it will compile this new solver depending on your system. It will take some time. So it compiled without any error. Make sure you are on the same page. I'm clearing my screen. Give me a thumbs up or something so that I know people are following. Don't clear. Okay, don't clear. This you don't need. This is automatic. I mean, why you are worried? If you have edit, okay, someone don't want them to clear. Okay, I will carry on. Notepad, exe. So let's say inside this there is another file. We are not going to modify anything, but let us just see that folder. So later on when you will have, let's say you want to couple your say Eulerian and Lagrangian solvers. So that time you may need to change your options. So here you are actually you just see the create fields and one C file, but actually it is with this options we are actually locating all the files that are present in the source folder of finite volume include and mesh tools on all the libraries in the finite volume and mesh tools. So later on, let's say you want to incorporate a turbulence model, you need to source the turbulence thing, you need to say Lagrangian multiphase model. If you see those solvers, you will see few more lines, and you can you can estimate that how you are going to modify your own solver, whether you need to incorporate new things or remove some things. So this is very basic thing. We just need to add equations, so we don't need to add anything here. I'm closing it. Okay. So we have done that wmake thing. So now we can edit in the create fields. Notepad.exe. So in this file, what are the things I need to add? Can anyone tell me? I need to add a temperature equation. Come on, notepad.exe. So I need to add a temperature equation. So it will have a material property that is thermal diffusivity. So for that, I need to, and here you can see it, the OpenFOAM in this file, it reads the files through input-output dictionary, that is transport property. In the transport properties, it is actually reading already a user-defined function, user-defined value of uh, dynamic viscosity. So similarly, I will add a thermal rigidity term. So I will just copy this and paste it here. And let's say I rename this new variable as dt, and in the transport property it will be read with the term dt. Dimensions are same as dimension of viscosity, so I don't need to change there. Here also look up for the term dt. These changes, if you have made, then you have incorporated, we have added the variable thermal diffusivity. So this is an input output dictionary, how you read take values from user. One way to check define a variable. Now let's say there is another way to define the variable. Density we are solving incompressible. So we don't need to worry about density here. And it is not a dynamic viscosity, it is already kinematic viscosity. So let's say the other variable that is independent variable that there's we have already pressure and velocity. So you can see the one is a scalar value and one other is a vector value. But you can see the syntax. Remains same. Just in the first line, you need to define volume scalar field, volume vector field. Another is this the size and all, in which variable, in which mesh you're defining the variable. These things are taken care over here. And then you have some options over here, input output objects. This is needed whether to read the boundary condition and whether when you want to get the output. So the first thing is, if it is must read, then it means that it will ask for a boundary condition. The other option is no read, then it won't ask for the boundary conditions. And auto write or no write. If you don't want to get save that as an output, you can keep it as no write, and otherwise keep it as auto write. It will automatically, based on your control field dictionary, what you define in your control parameters, it will write. So what we are going to do is we are going to copy this, because temperature is a scalar field. Let me copy it from the pressure field side. Okay. I'm replacing the P with P. That's it. People followed? I'm going to close it. So we have added some new variables. So one was independent variable t, and one is like user defined variable, that is dt. So after that, I will go to notepad exe and change add the equation in the my form. See. Okay. So where I need to add this temperature equation. So if you see here, I mean, before this, this is the main file, main solver uh, run directory. So this is a main function. And before this, it's like you set the initial conditions, you calculate the initial continuity error, create mesh, create time, set up your control parameters, and set up your root case file so that you can do the post processing things. And from this line, your time loop starts. So can somebody tell me where should I add this temperature equation outside the time loop? Where should I add my temperature equation? Here I have controlling the concurrent number. From that, I am calculating the delta t. Here setting the u equation, solving the u equation, and this is the piso algorithm. So I will maybe in the slides I will discuss with how this piso algorithm works. So once you get the pressure and u equation, so we are solving temperature as a passive scalar. So I don't it need to be incorporated in the like piso algorithm. After the piso algorithm, when I will get my U and P field, I will add the temperature equation inside the time loop so that it solves at every time. So what I'm going to do is again I'm going to copy this every scalar function here, paste it over there. But I need to modify these changes. So it is a big dilation t, something you can do previously and add before also. So FBM ddt, that is the dt term for temperature, and the FBM divergence term for temperature, the volume flux phi, temperature T, and then Laplacian. So Laplacian should be yeah. People followed, and then I will rename this equation as T equation, and I'm going to solve this equation. Right. I will give some time here, people, to add. If done, then I will save this.
Krishna, can you repeat that my foam editing once again?
So, like the description of the solver that I said something.
Yeah, I mean the editing that you did. Someone lost his
Editing only.
Yeah.
Editing. So after this, like after this piso loop, I am getting my velocity and pressure field. So, and I want to solve my temperature equation inside the time loop. So after before this runtime, right, and after getting the velocity field, that is piso loop is ending over in this facet. So after that, I have added this temperature equation here. You can see this is the non-orthogonal loop, and before that, it is the piso correction loop that is ending over here. So after that, I am writing the temperature equation. There
Deepak,
is no source term in this temperature equation for simplicity. Okay. So in this, I am solving the temperature without the coupling. So if you want to do the coupling, then I think you need to add a source term in your U equation. Here you will some term will come with a function of t, and also if you have added something here, then you need to take care of that in here also in getting the fluxes here. So that modification also you need to do, and then you will have a coupled velocity and temperature function solver. So if okay, then I will close this file. Good. So I have added these things. So I have done the modification in my solver. So let's do W may compile it once again. So let's see there is no error. Yeah, I am hitting problem. I'm clearing it. So from here, now that I have made my new solver, I need to define a new case file.
Hello, Mr. Krishna.
Yes.
I'm getting an error.
What error?
The error says permission denied.
Okay, so then you might have app user bin. There you need to modify also. Notepad. In the make folder, the files. Here you need to make it own user app. You make sure you do this change.
Can you please zoom it a bit? I mean, I'm not able to. Yeah, okay, 1 second, just. Thank you.
So good, all of you made the solver. So let's go to the run directory to make a case file for this new solver. So now I'm in the run directory. So I will again copy my cavity case and modify in there. So I will copy it from phone tutorials. Incompressible. Cavity, cavity, and let's say I copy it to my cavity. So let's check it. My cavity is there. So let's go into the my cavity. So what are the changes I need to do here? Can somebody tell me? So first of all, I have defined a user-defined function that is dt. So I need to define it somewhere, right? Modify txt. That is in the constant property file. Constant transport properties. I need to define dt term here, and the dimensions are going to be same as that I have taken care previously. And let's say previously in the previous case I have forgot it. So I keep it 2e minus 3. But let's say, I mean, in the previous case, I have not made those changes. So for me, I will do this 4e minus 5. That was previously when I run the cases 4e minus 5. Okay. So, and then I need to change this to tt. Okay. You people followed? At this line? Yes. So I think you people did this, right? So what are the changes again I need to do? Can somebody comment? I have defined a new equation. T file, yes. Other than that, we will do that later. Other than that, I have defined a new equation. So for this new equation to solve, I need to define the boundary conditions. Yeah, okay. I need to define the schemes and solver also. So to do that, I will go and edit my schemes. So what I need is I have defined a divergence term for temperature. So for that, I need to copy this. I have this IT term in my equation. So for that, it is this. And let's say my divergence scheme for temperature will be up. Okay. So after this, Laplacian scheme, I don't need to, I mean, I can define separately like Laplacian dtt, but by default it is Gauss linear orthogonal, and for all the Laplacian's command, it will take that orthogonal, and that is what I want. So I don't need to add the Laplacian scheme here for temperature. So let me close this file. if you guys are done till here. Yes, no? Good. So after this, I need to define a solver also for this solution. So the new equation need the algebraic equation that will be created. I need to define a solver for that. So for that, I will copy this u whole command. Do this here. T. So the T equation will be you solve with this set of commands. Smooth solver, a smoother. Let us replace it with Gauss Seidel. Okay. Rest of the things say as it is. I think I need to define T final also. So I will do that. If not required also, it won't harm also. So T final is defined. These changes if you have done, then I will close this. I have defined a solver for the temperature equation. In Notepad typo error, so OpenFOAM, I mean Notepad won't know what you want to type. So, and I don't think Notepad will tell you that. The typo error type and all those things, I mean, once you will be like getting used to it, use it frequently, those things won't happen. So don't worry about that. So I'm saving this. So now boundary conditions that you people told me, I need to define that. I go inside the 0 directory. In here I have this u and p file. So I will copy this p file to a t file so that I don't need to like create t file again. So just little modification I need to do in the t file. Notepad. So what are the changes I need to do? This looks easy. P should be T. After that, dimensions. The temperature equation. And it is like the previously that without source term that we have done the case. So let me keep the boundary condition same as that. So I will define it as 300. I will define this as fixed value and then value into uniform. So okay, make this 300. So I will give some time here. If people have done them, okay. Everybody following?
Yes, sir.
So I will close this. Control date and block mesh. I have not done any modification, not required. So I will run the case now. Block mesh, my foam, because the new solver is named as my foam. So to run this new solver, the new command will be my foam. Done. So, okay, the time question, time also is different, so maybe we won't able to compare it, but still. So you can see that we have this solved for T. We have solved for the temperature equation. You see like that, we will do this result and check it in the paraform. So let us delete this first. My quality result form. Pressure is like this. Temperature. So I think I made a mistake somewhere. This temperature file should not come like this. Can anyone guess where is the mistake? I think I should change in the solver itself, the Laplacian. You don't need to repeat it, like the process is done. So let us see if I do this change, what will be the result. Meanwhile, if you people have any doubts, you can shoot on me. So I just made the modification of Laplacian term that is negative to positive. So those changes, let's see what will be the result. So
Delete the other result. Dot form.
it is overwriting. So this. So now you got the procedure right. So how to modify it and all temperature. adding equation, user defined variable, and adding the equation. So maybe I need to like check once again what is the equation and all. But that is the overall procedure. Let me just go in the folder here. Sure. It was negative. So the previous term was already actually right. Anyway, so you have created the solver, right? So let me show you some of the like glimpse of the codes. So
Someone is asking me, why didn't you change the control dict?
control
My
dict
my
is
application in control dict. I
my
don't.
application because I am running directly
Yeah.
through the command
So
my
you
phone.
you need not to change it, right? If you're
Yeah,
running
you
directly.
don't have to change it. If you want to run it through your that shell files that you create, all run script files. Then in that you use underscore get applications. So if you want to use the script file, then you need to, then you need to read that application folder. So there you need it if you want to do that. So I have some glimpse of other codes that you may find it anywhere in the CFD online and all, but it will help you to accelerate. So how you can do your coding, like the first thing you need to a cell loop. So in here you can see how a cell loop is written in your code, how a face loop is written in your code, and how you can loop over the cells and the faces inside it. So that is the code. So you will have the video. So you don't need to save it or anything. This is how you do it. Already in the previous tutorial, people have defined how you can use a defined function boundary condition, but I also included it. But let's say you have some mathematical functions inside your boundary equation, then to include those functions, then you need to make, then you may use this snip of code. So this is a sample of that. Any questions you can ask? Feel free to ask. So let's say another function that I want to write is to, let's say I want to get an output functions. I want to get the output of, let's say, kinetic energy of the system, and also I still want to get the dissipation energy of the system. So here you can see that the first line is actually when you have parallel processing, then you use this to get the total number of cells from counting all the processors. So that n cells is the total number of cells. The sum do the summation of the velocity vector field in parallel, and you get an average U bar. So some example only the motive here to just show you some example where how you can proceed and how you can do these things. So that is my motive here. So to show you, you can define just inside a volume new scalar field just inside the code itself. You don't use split fields also. In the volume scalar field, you can use the u component, x component to define a new variable ux, uy, and then you need to know that once you copy, once you get a gradient of a scalar field, then it becomes a vector field. So to save that, you need to define a volume vector field. Similarly, to get when the magnitude of the vector becomes a scalar. So some snapshot that I am showing you here, and a cell loop to calculate the kinetic energy of all the cells and the dissipation energy of all the cells. And this is a for two-phase flow, so it is alpha one is the volume fraction, alpha and one minus alpha. So and then I have to save that files. Let's say if kinetic energy, so I have already in the solve here I have already defined a pointer for kinetic energy. So this is the snapshot of how you can get the output in a file with the file name, let's say kdat. Just inside the time loop, if you can keep it, so then at each time step you can get that. So this is not big thing, just a small snapshot how you may accelerate your work. Other than this, any doubt if you people are having, then you can ask. I can show some more codes. Uh, let's say sometimes you need, when you define the equation dimensions, OpenFOAM works with dimensions. So sometimes in your equations, you may need to uh, change, add a dummy variable which will change the dimension of your equations. So let me show you how you can do that. So here I have my solver already. This is interFOAM. Will show you in the create field. So, so let's say here I have this. Show you how you can define a dummy variables. So let's say beam change, beam scalar. So beam length, this will be of dimension length. Otherwise, you can in the bracket inside you can define the all the fundamental dimension and define a new variable with given dimension. So once you how you will modify it, let's say in an equation. So so here you can see that I am adding this dummy variable because my level, this is equation for level set scalar for multi-phase flow. So for that I am adding this because the gradient it is delta t, the grad function it is multiplying with the grad function, but the variable is non-dimensional variable field. So I need to divide it so that the gradient and the multi-division will lead up to a non-dimensionalized variable. So this is one way. I mean, very frequently, actually, you need to do these things once you develop solvers. That is a given name for my solver. Uh, I- that is, I'm just showing a tutorial. It's not uh, meant for you to do it. That is my customized solver. You won't find it. So if anything, you may ask, or I will ask. So then I can show you how you define what is ISO algorithm. Now that I have time, then I will describe it. That so in the equation that you see in the icoFoam, the first equation, the first thing that you see is the U matrix was solved. So in that it is defining the matrix without the pressure term, which will lead up to a matrix form of this. And very frequently you will see terms h by a and all in all your incompressible solver at least, which is h is here is the residual part, which is b is uh, source term of the u equation minus the non-diagonal terms of from the matrix of the u, which is defined as the h. And h by a will be the diagonal term of u when divided by h by a is there. So to solve the u equation, when you solve it, you add the source term and you get a predicted velocity field, which will be just solving this h u minus directly by a diagonal term of u. Okay. So and then in incompressible flow, I think you all might be aware, like we have this continuity equation which converts to Laplacian equation for pressure. and it comes from this equation. Like when you do the integration of this continuity equation in the control volume, it changes to a divergence scheme and sf.uf, where then the predicted velocity field, if you keep that uf, which will be interpolated from the velocity field calculated previously. So if you do that, and then you will get the Laplacian equation for pressure, which we solve in the P equation.
If someone has doubt, they can ask. So someone is asking you, can you explain the part where you edited the myfoam.c file to add the T equation?
Okay, so let's go to the location. So here, here you see the time loop is beginning over here, and here I am defining the U equation that I said without pressure curve. It is defined over here, and then we solve the equation with the adding pressure as source term, and then first of all I get the AP, like that is the diagonal term of the U equation matrix that is stored in here, and then this is the H by A term, and then we calculate from this vector field, it is just a velocity field, and then we calculate it as flux pi by al, and you want the temperature. So after the solving of the non-orthogonal part, non-orthogonal loop, and the piso loop is ending here, so I am adding temperature equation here, so that it is inside the time loop, but after getting the velocity and pressure field. Start. Yeah, this is the here we are, like somebody sometime asked like what is the error that it is representing continuity. So this is the file where you calculate the continuity error, and it should be less than, let's say, 10 power minus 8 or as less as possible, so that your system remains stable. Any more question in this isoform? What is this FBB flux is doing? Can somebody tell me? So the flux is nothing but u dot sf vector. So that is what it is doing. And once we get the flux, again we have this term here. And that is for, like, say, because you are interpolating the point velocity field to the phase velocity field. So the interpolation had to have some error. So to reduce that error, we have this additional term. At just phi, constant pressure, these are for the various boundary conditions to remain stable and consistent. So we need these terms, these lines here. That you remember sometimes, like in the fluent, we defined the external pressure field. So that is what also defined in OpenFOAM also. That line is over here, equation set reference. For the given reference cell, you define the reference value. Flux is calculated after the pressure correction step. And the velocity is updated. So I'm closing it. If anyone have any question, then I am here. You have to search it. Spend some time. Actually, you people are doing great for like for the 3-day workshop, but to get the glimpse of all the solvers, You need to spend some time and read some tutorials, some files. So Chandan Bose sir shared some links, right? You can go through the links. Other platforms are CFD online, and then OpenFOAM has its own user guide. So you can go through that, and then you will get the idea of solver that you want to. A book or instruction manual to write our own solver. I think Chalmers website is very good starting point for the basics to start your own development, code development part. So you can go to that website. They're giving a lot of tutorial on how you can merge one solver with another. And of course, Fosi is also having a lot of good tutorials and very good case files. Good phase field modeling means multi-phase flow or phase change. Deepak. Okay. Solidification of metals. I think it will be phase change problem that you have the solidification part. So I think most of you have the question like which solver to use, and to get the idea which solver you need to work on. So actually you can just in the OpenFOAM website, there is a description of all the solvers, basic solvers, what it does, and from that you will come to know. And actual answer to this will come with experience, like, and related to your topic experience. It will be a plus if you have the better understanding of C++, but to do like basic amount of coding, like defining the user defined condition and some snapshot of your code, you can start doing it, and once you start doing it, you will automatically learn. So start doing it, and you are good to start. I mean, basic with little knowledge only, you are able to start. Reference regarding solver, which solver? I mean, there are a lot of references for a lot of solvers. OpenFOAM user guide will be a good starting point for all of you. Okay, I will share that link. Yeah. One link which actually this gives the description of all the solvers. I will share once this presentation and my session was later on.
Okay, so I hope there are no more questions. So we can take a tea break of 15 minutes. So please come back by 3:40. Then 3:45 we will start with Mr. Divyesh Varia's session.